We now start a new chapter called the system of particles and rotational motion. Okay, till now we have been dealing with point masses. What is a point mass? Where we say that all the mass is concentrated in a space that small that its length, breadth and height is all nil. Now obviously that is not possible. That is simply not possible. Even if you have a sphere, okay, say even if you have a sphere which is very small, okay, very small, there too you understand that the mass is a distributed one, correct? And something like a point simply does not exist. It does not exist. But till now, whatever we have done, whatever we have solved, that is all related to such kind of point masses. It deals with the point masses, and point masses do not exist. So we look at a car. Okay, what we'd like to analyze? We'd like to analyze a car, say, and we see that it is not a point mass. No, even if the passengers are not sitting in, say its engine is in the front, okay, then there are seats and there are so many things which have a distributed mass. Now this distribution of mass, that means there are multiple particles present and the mass is distributed. That means it is not one particle but a system of particles. It is a group of particles. Okay, we are not talking about a point mass. We never do. Now that will immediately take you back to everything that you have learned, right? We did all the collisions and the Newton's laws of motion and whatever we did till now, that there we assumed that the mass is a point mass. Now I don't know how things will behave, how these laws will hold when I am dealing with a system of particles, a distributed mass kind of thing. What happens? Okay, that is what is the subject matter of this chapter. Okay, so what has happened from the point mass? Earlier we thought all the mass of an object is concentrated in a point. Concentrated in a point. Okay, but in real life this doesn't happen. This never happens. We know it never happens, right? We know this does not happen. In real life, the objects have a distributed mass. They have a distributed mass, right? This pen, I cannot say that all the mass is concentrated at one point. No. The mass is absolutely distributed. There is some plastic here, the same kind of plastic continues here. So why should I be favoring, say, this end or that end? It has a distributed mass. It's quite visible, right? Now the trouble is, we have been taught all the laws that we have done till now, we have done it on the basis of a point mass. All the collisions, point mass, right? Till now all laws have been explained with respect to a point mass. And this is the biggest trouble. Nothing in this world is a point mass system, and we have studied everything with respect to the point mass system. So what do we do? Where do we land? What do we do when we apply these laws in the real life, and what will happen? Fine? That is what we'll explore. But before that, the kind of objects that we are dealing with, they are nothing but rigid bodies. That is something that is important. Those masses that we are seeing, they are rigid for us to be able to analyze them right now. So those system of particles that we are dealing with now, we'll assume them to be a rigid body. And what is a rigid body? What is a rigid body? Rigid body is, what is a rigid body? Rigid body is something that does not change shape, obviously. Right? That is rigid. So, yes, the body that doesn't change shape or size, on application of force. Now this is quite a layman kind of definition, but this is the commonsensical definition that you should be able to come up with, right? And when I say layman, do not take it to be a derogatory word. That is the commonsensical kind of thing that anyone comes across with. When we are studying physics, what do we say? See, if this is a body which is a rigid body, then what we want to say is, you apply what? How do I know that it has not changed its shape or size? How do you know that? Huh? How do you know that something has not changed its shape or size? You apply force, then what do you see? Whether it has changed shape or size. Our perception of shape and size is quite different from what actually might have happened. No? For example, have you been to a well? No? A well from which you draw water. There the people take their earthen pots and put it on a stone, okay? And gradually you'll see wherever they keep putting their earthen pot, gradually that actually gets de-shaped and becomes spherical. That means what has happened? That earthen pot has been abrading it. It has been taking away some part of the rock whenever it was put. It has not happened in a day. It might take a year, 2 years, 3 years, right? But somehow this process must have been a continuous process. That a thing as soft as an earthen pot has been able to make an impression on something as hard as a rock. And it has not so happened that the millionth person put his pot there and suddenly he saw that there's a spherical thing. No. So it must have been happening day by day. So you put the pot, something there must have changed. That was not visible to you. So how do we define it in physics? Suppose there is a particle 1, okay, a point 1 here and another point 2. You apply whatever amount of force, the distance between them does not change. That is our definition of rigid body. So what happens? The relative position of the particles doesn't change on application of force howsoever high. Okay. Now we very well understand that is not possible. There is nothing in this world that will not break under some tremendous force. Fine. So there is nothing like a perfectly rigid body. Okay. But there is nothing like a perfectly rigid body. You understand? Huh? You see the humor. I define something, then I say it does not exist. Then why did you define it? That is the ideal case. Okay? So, how rigid or not rigid something is, that we'll measure with respect to our perfect definition. The definition for the perfect rigid body. We get the point? Fine. But there is nothing like a perfect rigid body. Still we are defining it. That is the ideal case. Fine. Now, once we understand what a rigid body is, we'll try to see what are the motions that are possible. What kind of motions? Okay. Motions of a rigid body. Motions of a rigid body. What kind of motion can a rigid body have? You asked something. What kind of motion does a rigid body have? Now, till now we have been dealing with one kind of motion, that is called translational motion. That is called translational motion. Okay, that is called a translational motion. What is a translational motion? How do I define this? It is kind of the linear motion that we see in everyday life. So you slide a crate, it is a translational motion. But how do I define it? How do I define it? See, at times when I start defining these things, you'll feel we are going a bit too far in being so precise. But the fact of the matter is we are not. Because each of these specific things will define what we are trying to say, and that's how we proceed in physics. It is an exact science. Correct? So, when do you say that something is translating? And why are we trying to do this? We are trying to do this because there is some other kind of motion also that we see, that is a rotational motion. There is something called translational motion, there is something called rotational motion, right? So so I drag a crate, that is a linear translational motion, right? But there are so many things, even when we are unconsciously there are so many motions around us which are rotational. This fan, this AC, right? You walk, you are also kind of, your legs are undergoing a rotational motion. They are not translational motion. So many things around us are translational as well as rotational, but the translational is something that is understood to us in a simpler manner, and rotation is something that we normally do not understand. Fine. So when do we call a motion to be a translational motion? When all the particles of the body, when all the particles of an object move with the same velocity. And what kind of object? What kind of object? Rigid object. So it is a rigid body. If they move with the same velocity, okay, the motion is called translational motion. Fine. It is called a translational motion. Translational. Important to understand. Example, a sliding crate. Example, a sliding crate. So now we come to a rotational motion. What is a rotational motion? Now let us try to understand. We have a small top, or maybe you cut a circular, not necessarily circular, but I am starting with circular. You cut a circular cardboard, in the center you insert a pin kind of thing that does not rotate, you somehow fix it and you give it a spin. Okay, you give it a spin. Fine. I am looking at it from the top, so I'll see a circle, right? That is rotating, obviously. So I'll see this. This was given a spin, right? So it is rotating. Now what happens? I mark a point A out here and a point B out here and a point C out here. Okay. Now what do I see? Suppose in a time capital T, they complete one round. Fine. They complete one round. So what happens after that? What do you expect? Since it is a rigid body, this point will come back to the same point. The point B will be back to the same point. Why? Again, it is a rigid body. It is a rigid body, so the distances do not change even when you are applying some force, and here you are applying no force in a sense. We have defined that it is called rigid when the relative positions of the particles do not change. So obviously it should not change. Okay, so it is there, and the point C is here. The point C is back to there. What is the time they have taken to complete this circle? The same time. All of them have taken the same time. Now, which has moved a longer distance? C. In the same time, C has travelled a longer distance. C has travelled a longer distance. So the velocity of C has to be the highest amongst the three. Between these three, the velocity of C has to be the highest. We understand that. See that different particles, they are moving with different velocities, and farther the particle from the point around which they are rotating, the faster it is moving. Correct? It's not called center. Okay. So what happens here? Different particles move with different velocities. Okay. That is number one. So that is number one. Now, see, as I start coming closer to that point, what happens? The particles start moving slower and slower and slower and slower and slower. Is it not? As I come closer to it. What happens when I go exactly on that? No speed. Okay. Now, if it was a solid body like that, try to think. And this whole thing was rotating like that, then all the points that lie on this line, they are stationary. Everything else is moving around them, but they themselves are stationary. This line on which the particles are stationary is called the axis of rotation. Okay, that is called the axis of rotation. The particles lying on the line about which everything moves are themselves stationary. Okay, and this line is called the axis of rotation. The axis of rotation. Okay. The body, about the axis of rotation, the body can be symmetrical. Say you have a cylinder, you take the center line, you rotate things, it is symmetrical, or it could be absolutely unsymmetrical like this. It is not always necessarily symmetrical. Understand? So this is called the axis of rotation. Farther, so now what happens? All the particles do what? When they move about the axis, they are actually going in a circular motion. Okay, all the particles traverse in a circular motion around the axis of rotation. Okay. Around the axis of rotation, they traverse a circular motion, and farther a particle is, from the axis of rotation, the faster does it move? Fine? That will always happen. Fine? You understand? We'll next chart other type of motion.